Brian McAllister. I'm not giving the talk. First of all, I'll just mention a little, I know a lot of people here are actually work in this building, so you know all this. But for everyone else, Groupon, we do business in 48 countries. We have about well, you can read the numbers. But the key thing is it's only a 4-year-old company. We're still building lots of really, really exciting things. We have all the systems of a 4-year-old company, but magnified a lot. There's a lot of exciting problems and a lot of exciting things we're trying to learn about. So engineering here, we're going really fast. There's about 900 some of us now. We're approaching 1,000. 150 of those have been hired, just this, well, not this quarter as it breaks over, but you know what I mean. Back a little bit. We're in the process of killing a lot of our big monolithic stuff, moving into services, building out all of this fun distributed infrastructure, and we work with, we have big dev offices all over the world. So it's a fun place to be. And with that, I'd like to introduce Julien Le Dem. Got it right. I did get it right. Talking to us about Parquet.
Thank you.
There was one other thing I wanted to say. If you're not from this building and you want to get on the Groupon mobile Wi-Fi, that's the password. Of course, you should be paying attention to the talk. It's fun to have internet.
Test 1, 2.
Hello.
Hello.
I'm Julien, and I'm the processing tools lead for the analytics infrastructure at Twitter. And I'm going to talk about Parquet, our columnar file format for Hadoop. So first, I'm going to give you a little bit of context. So at Twitter, has been published, we have over 200 million active users, and they produce and consume over 500 million tweets a day. And so the instrumentation of the website and getting information about what they're doing, how they're doing it, it produces a lot of data, over 100 terabytes a day of compressed data. So that's a lot of data, and just storing this data and analyzing it, it's a lot of work. And so to do that, we have several, more than 1,000 nodes, Hadoop clusters, and we build a log collection pipeline and the tools to do the analysis. And the role of the analytics infrastructure team is really to be a platform for the whole company. And every team in the company uses Hadoop in one way or another, whether it's for like doing some core analysis, or for doing spam detection, or for doing who to follow, or other kinds of features based on that. And our role is really to look at the cluster as a whole and make sure we do make good usage of the cluster. So to give you one example of how we do store logs. So we have a log collection system, and the logs show up in HDFS, and it's stored mostly using Swift. So Swift is an IDL defined at Facebook, and it lets you describe the type, the schema of your data. So you can have deeply nested data structures, and each field can be a struct, a primitive type, a list, a map, and so recursively, right? So basically what you could define as a struct, you can define. So to give you an example, one of our big schemas here has total 87 columns and up to 7 levels of nesting. So quite deep and quite wide, and a lot of different types in there. And if you see here, you have things like transaction ID, IP address, country, different types of things like what you would expect in instrumenting your website to know what's happening. So the goal of columnar storage is really to improve the I/O, because Hadoop it's very good at running big jobs, and it's reliable, right? You're going to lose machines or disk, a lot of things are going to fail, but the job is eventually going to succeed. And you can run very large jobs and they will finish independently if machines fail. But it's not very good at low latency queries. When you run your query, it's going to take a long time before it finishes. And so the goal of Parquet is to incrementally take advantage of columnar storage into the existing framework, right? Integrate with Pig, with Hive, with cascading, and scalding, and all those existing stack, and gradually add all the features that exist in the big parallel relational database, like Vertica or similar stuff. And so take some of those technologies, how you do better storage for queries and that kind of things into the existing stack. And so to that goal, it's not tied to any framework in particular. Like a lot of things in the Hadoop ecosystem define schemas like Thrift, Pig, Thrift, Hive, Avro, protocol buffers, but Hadoop doesn't define any of those things. So the goal was to be interoperable with all those things and to have a unified storage format, columnar format, that can interact with those things. So, columnar storage, that's a mandatory hidden feature in any big data tool. And so the goal is to limit the I/O. So when you're doing a query, so we have this data set with 87 columns, but most of the time when you're doing a query, you need only a subset of the columns, right? You're aggregating per IP or counting how many queries for that event or those kind of things. So really, out of those 87 columns, I need to access 2, 3, 4 columns to do my aggregation and counting. So the goal of the columnar storage is first to limit the I/O to only what you need to access when reading the data. And secondly, it's going also to save space because now, because we organize data per column instead of per rows, it's going to compress better. And for two reasons. One reason is because we know the type of this column, we can use an encoding that is more efficient, and it doesn't have to be one value at a time. It can encode multiple values at a time. For example, if you have integers that are smaller than a certain value, you can do bit packing, right? Okay, so this integer is going to fit on 5 bits. I'm going to encode it 5 bits at a time, and because I'm doing columnar storage, it's easy to do that across rows. And also it's going to compress better, because let's say you apply either Snappy or LZO. It's going to compress better because now you're putting all the data of the same type, which is like uniform, next to each other, so it's going to compress better. Instead of compressing one row that is heterogeneous, you're compressing a column which is much more homogeneous. Like if you have a column that is a tag or a status or something, so you're going to have a lot more repetition, it's going to compress better. And also, it enables vectorized execution engines, and that's like the future thing, right? We start by integrating this into the existing stack, and then in the future, we can enable execution engines that are vectorized like Drill, and Drill is working on that, which is another incubator project. So if you have questions, feel free to interrupt or ask me questions. So this started as a collaboration between Twitter and Cloudera. So Cloudera is working on Impala, you all heard. Yeah. So Impala is a SQL engine, so it's based on top of the Hive metastore, and it's built to be compatible with Hive, and you can run query on Impala. It's going to be much faster because instead of running it on MapReduce, they're going to run it on their own service that avoids this intermediary checkpointing into HDFS. Right? When you run a Hive query, it's going to generate a plan and turn the SQL query into a sequence of MapReduce jobs that are going to do checkpointing in between each jobs in HDFS. Right? So you have a lot of I/O, reading from HDFS, writing to HDFS, reading again and again, with a lot of synchronization point where before you start the reduce step, you need all the maps to be finished. And before you start the next MapReduce job, you need all the reduces a lot of synchronization steps that add a lot of latency in the query, and also a lot of I/O based on the checkpointing between steps. So
what kind of compliance? Like, is this SQL 92 compliant?
it's Hive QUL compliant. So Hive is one of those SQL-ish thing. It's mostly SQL, except for some non-standard extension. So that's Impala. Impala is, the goal is to be compatible with Hive, and Hive is not compatible completely with, I think, the
SQL. Yeah.
with SQL. But Parquet is a file format, so Parquet is the thing you use to make your execution engine faster, at least for reading the data. And so the idea is, so Cloudera was working on a prototype of a new columnar format, and we were working on a prototype of the columnar format because there was not quite anything that was good for needs. Like, we wanted to support nested data structures, so really being able to be columnar all the way down, because you don't want, like, instead of 87 columns from what I showed you, we would have had 10 columns, and like 9 of them would have been struct with like nested data structure in it. So that would not have been very efficient from that point of view. So really there was nothing at the time that was doing anything nested. And that was quite fixing that thing. So we collaborated and designed this, and Impala is all about C and generating native code. So for that, Parquet is compatible is like language independent. And we implemented all the Java side and being able to read it from Java. So the interesting side effect of that is the format is formally specified and language independent because we need two distinct implementations in Java and C. So some initial results. So we do have Parquet in production at Twitter. Our two largest log categories have been converted to this format, and that way we save space. So you can see that after conversion, so initially we were using Swift in the strict binary in compressed blocks. So applying LZO conversion on top of strict binary, so it was already a pretty compact format, it was not text files. And we converted that to Parquet, and by doing so, we saved 28% on the space, and on like hundreds of terabytes a day. That's a lot of space saving. So the first aspect is saving space, and then the second aspect is how do we improve our scan time. So on this data set that I took for the example, it has 30 columns. And so if you read a single column, it takes about 10% of the time it will take to scan the entire data set. And so the blue line is the original scan time with the original format. And because it's oriented, you know, whatever you access, the scan is the same. You scan as much data. And with column-oriented, when you read only one column, it takes 10% of the time. And if you read all the columns, we had a slight overhead of 10%, which comes from, you know, reassembling the record. And we believe that we can still make this faster because we're also scanning less data. So we save on I/O because it's smaller than original. So we should be able, you know, to improve performance so that we actually are faster even when we read all the columns. But even though the overhead is still reasonable compared to the main use case when you read actually a subset of the columns.
So because you're compressing it and you're using column storage, is this splittable? Like, kind of the same
Yeah.
way all the others?
So similar to RC5, it's in raw groups. So I'm going to cover that a little later in the presentation. But basically, you have a raw group, and each raw group is in columnar format. But each row group can be a different split. So this is configurable. Basically, the row group, you can make it about the size of your block size in HDFS or smaller. And the row group is the unit with you will scan, right? That's where the columns are scanned. So yes, it is splittable. And so that was with the plain encoding. And we also implemented dictionary encoding. So dictionary encoding is when a column has low cardinality, you have few distinct values. And by few, I mean, a few tens of thousands is okay, right? You can build a dictionary, and instead of writing the strings one after the other, you just write the IDs of the dictionary, right? You build that dictionary, and you can do a lookup when you decode. You do a lookup, so you save the dictionary once, and then when you read, you do lookups in the dictionary. And because now you store it as integers, same thing, right? You know the maximum numbers of entries in the dictionary, so you can use bit packing to store them more efficiently. So the advantage of that is when a column has lower cardinality, instead of using more heavyweight compression like LZO, because LZO or gzip is very expensive to decode in CPU, and LZO is less expensive, but still it's an overhead. Instead of using those that are pretty heavyweight compression engine that try to compress bytes without you telling them anything about it, you can do very lightweight compression using dictionary encoding. Actually, that works pretty well because in green, so I took out of those 13 columns, I took those 13 that were dictionary encoded, that had low enough cardinality that they would encode with the dictionary. And in green is the space they use in plain encoding in Parquet, just writing the values one after the other. In yellow is how much they take with dictionary encoding without even compression. So dictionary encoding compresses better than just heavyweight compression that is more expensive CPU-wise. And if you add the LZO on top of it, which is the more heavyweight compression, it compresses even better. And you can see that you have similar meanings on the scan time, that it takes half the time to scan those columns once they've been dictionary encoded, because it's much faster to decode them. You read a lot less data, and it's really fast to decode them. Yeah?
So, do you have separate cluster for this, or is it on top of the GFS?
So Parquet is a file format. So it's really just storing file in HDFS. There's no service, it's just a file format. So it's just storing files in HDFS. Yeah.
Okay, and one more thing, like you're talking about the columnar storage, right?
Mm-hmm.
So we have other databases like existing technical that are analytical, and we're talking about the scanning the whole column, not partitioning it, right?
Yeah, it can be, well, so this is a file format for Hadoop, so one of the main things is it's read-only, right? You generate the file once and then you're going to scan it. And but it's then partitioning, usually we do partitioning per hour, and then it's like different files, it's at the directory level.
Because just what you can do is that, you just divide it into one scan and you can go to the particular column and then specify your key and you can scan to the particular column. Then
Yeah.
you get one particular partition and you can scan very fast. And moreover, you can do two options, you just read only. So,
Yeah, so this one is not, the goal is not to enable CRUD operation or like any imitation. But still you could do indexing on top of it. So you still have the notion of being able to go, so it's split in row groups, right? So in the footer, you know how many records are in each row group, so you could skip to given point in the file if you wanted to. And yeah, I don't know if that helps. We're also planning to add like statistics in the footer so that you could do predicate push down and read only the row groups that actually contain the value that you want. Like if you have minimum and maximum value for each column, for each row group, you can skip a row group if the minimum and maximum tell you that there's no rows in this row group that will match the feature.
because without partition, it will be very hard to calculate that will be very expensive in terms of time.
Sorry, yeah.
Sorry, I mean, without partitioning, what I'm trying to say is like, going through the millions of records for the same column, scanning would take a lot of time.
Yeah. So the goal here is to optimize for analytical query, like you're going to aggregate on a lot of data. So it's really to optimize for scan of a lot of records at a time as well. Like not too much for doing random access. So yeah, so that's for showing that techniques like dictionary encoding that you can use because now you're compressing one column at a time. They're very efficient in some cases to compress the data further. So the format, as I mentioned before, so the file is split in row groups. Each row group is in columnar format. And the reason for that is when you write, you need to buffer an entire row group in memory because you're receiving the data one row at a time, right? And you want to write it one column at a time. So you need to buffer the entire row group in memory to be able to write the first column once you have all the data for it. And then each row group is made of column chunks. A column chunk is the chunk of that column inside that row group. And each column chunk is made of pages. So we split even further each column in pages, and then the unit of compression. Each page is passed to the compression algorithm. And basically that's the unit of access in a column. When you access a row, you're going to decompress the column, the page that contains that row, and get to the point on that page. Row groups are made of column chunks that are made of pages. And if you want to tweak the parameters on the size of the row group and the size of the page can be small, but if it's too small, the compression algorithm is not going to be that efficient. So it should not be too small, but it can be fairly small. The row group can be big, but it has to be buffered in memory, so that's how much budget you want to give it when you write. Because if you're doing a conversion job, that's fine. You can use more memory. But if your job is doing other things, it's a query and it's writing the output, you probably want to give it less memory. And if you have a lot of columns, then you'd want to have a larger row group because now your scan, when you do a scan and reading only a subset of the column, you want to be able to read as much as possible contiguously to do an efficient scan. But if you have, yeah?
During the read operation, do I need the full row group's worth of memory as well if I was reading all the columns?
Yes, as well too. Because
Not just the column chunk, tiny number of size.
yes, so you need only the column chunk, the size for the columns you're reading. But if you were to read all the columns, then yes, you need the same amount of memory. And the reason is we want to optimize the scan. So you really want to read all that data at once in one scan. Right? Do an efficient scan, read as fast as possible, and then do the assembly on the data. Instead, and not doing seek of reading the beginning of the column, decoding it, and then going back and back. So yes. So it's like, usually these days you can give it a pretty decent amount of data. I think you can go up to a gig of memory, and it's not going to decompress the whole thing at once, right? It's going to decompress one page at a time. So you can still reassemble and not decompress the whole thing in memory. It's still going to stay compressed in memory. And it's just like a gig is already very large, and that lets you have good scans and amortize the cost of seeking on this.
So if you're using the dictionary encoding, is that dictionary stored in the row group?
Yes. So the dictionary encoding is going to be per row group. So the first page of that column in the row group will contain the dictionary, and then you have the values encoding as integers. And so that you load the dictionary and then you do lookups based on the ID.
Sorry, also regarding dictionaries. So if there is like updates in the dictionary, is there any mechanism like to actually update the let's say we add some rows and has some data that are not actually part of the dictionary? Is there any like mechanism to actually update the dictionary as well?
Yeah. So when it writes, so it's always the same thing, right? You add partitions, and the dictionary is stored per row group. So actually, the next row group can have a different dictionary, and that's fine, right? Because we're starting per row group. So if later you add more values, it's just the next file you're going to write is going to have more values in the dictionary, and that's going to be fine. It's kind of abstracted from the top level. It's still seen as string or other values.
So do you use your heuristic to decide what we'll build a dictionary for, or do you tag a column as?
No, so we use, so basically when we convert, we try to dictionary encode, and if the dictionary becomes too big, or if it becomes obvious that it's not distinct, you have too many distinct values, then it's going to give up and fall back to the regular encoding. So yeah, it tries to do dictionary encoding, and usually on the first page, it's going to decide if it wants to do dictionary or not. And at some point, if the dictionary becomes too big, it's going to give up. So you can have like the beginning of the column is dictionary encoded, and then the following is just in plain encoding because the dictionary is going too big. So there's like a mechanism we want to, so that you can write in one MapReduce job and still have only one pass on the data, and still do dictionary encoding.
Nice.
So we have, in the future, you may want to. We haven't implemented that, but it would be fairly easy to add like hints when you tell it actually those columns. I know it's dictionary. Those don't even try because even though it may look like at the beginning you can encode them, then they are too big. So that's a more visual representation of the format. So at the bottom of the file, there's a footer with the metadata and information about the row groups, where the row groups start in the file, for each column, where the column files in the column data starts in the row group. And it's written in the footer because you're writing the data, and so you're writing row groups and columns in the row groups, and you keep this information in your process while writing in MapReduce, for example. And at the end, when you finish writing, it's going to write the metadata about this information. So when you read the data, it's going to read the footer of the file and produce splits based on this information. So it's this information that makes the format splittable, because now you can split per row group. And the other thing we do is when you have a partition that has many files, what we do, we have a separate metadata file that is basically a summary of all the footers of all the files in that directory, so that when you start a job, you don't have to look up every single file, because the name node may be loaded. Every lookup of a file is a request is a name node, and then once you know where the file is, you need to request a slave where the data is, and you can randomly hit a bad slave that's going to be slow, and you may time out on the slave, or the name node could be loaded, or you may be doing a snapshot of your name node at that point, and the name node freezes. So that summary file reduces the number of lookups in HDFS needed to start the job and make it faster. And in theory, you could cache this metadata in a third-party service as well. Like some companies do that, like use a metastore to do that. And that way, those files are read-only anyway, so it's not like the metadata is going to be modified afterwards. And that saves like lookups that could be slow if you put it in HDFS. But right now, just having a summary file, just one file per partition, it works fine for us. So I explained how we have nested data structures, and I explained how we put it in flat format, and now there's a missing piece here, right? Because we want to be able to reproduce the record back when you read. So we need to store some extra information to capture the structure of the record. So we implemented the algorithm from the Dremel paper. I don't know, it's like the paper came out like 3 or 4 years ago. And it's about a file format that is used at Google to store nested data structures. So Google uses protocol buffers a lot. So it's kind of based on the protocol buffer schema. And they have this notion of repetition level and definition level to capture the structure of the record. So the way it works is definition level. So we have this example schema, right? You can represent the schema as a tree. And each column is identified by the path to get to this column. So we have one column per primitive type in that tree. And the definition level captures at what point in that path did the null occur. So was the links null or the backward field null, right? So that's the difference between, in that case, having a definition level of 0, 1, or 2. 0 means document is null. Actually, 0 means links is null, 1 means backward is null, 2 means it's actually defined and there's a value, right? And there's no 0 because 0 is 0. It's a record. You don't have a 0 for the top level, null for the top level row itself. And the repetition level, when there's a list, like in this example, links we have forward that is a repeated field. So basically it's equivalent to being a list. You can actually have multiple values in backward in that case. So here we have 10 and 30, it's like a list of values. And the repetition level capture at what point in that tree we have a repetition. So if we have 0, that means it's a new record. And so the value is actually in the next record. If we have a 1, that means in that case that we have a repetition here because links is not repeated. So we skip that, and 1 means backward is repeated. So you see in this example, repetition level and definition value. In backward, we have 10, which has a value of 0 because it was the first value for backward in that record. And then for 30, we have a value of 1 because it was repeated in the first repeated field in that path. So that's what that means. And that's how we capture the repetition of the field, the structure of the record. And if you want more details, we have a blog post on the Twitter blog about all this format and how that works and how we reproduce the structure of the record from those repetition level and definition level. So here I have another example. So you have 2 records and the schema, it's a list of lists. So it's like how do you do 2-level nesting of lists. So you can see the first record is a list that contains 2 lists. The first list has 3 elements, the second list has 4 elements. Then we have a second record. And so it's going to store them as follows, right? So you're going to have one data column that has all the values, A, B, C, D, E, F, G, H, I, J. Because in the columnar format, we really want a column where everything is the same type, so we can do efficient encodings like dictionary encoding or other types because everything is the same type, everything is homogeneous. And now we have a second column, which is a repetition level that captures the structure. And the same thing, right? We know it's an integer, and we know that the maximum value of that integer is 2, because we have 2 levels of nestings. 1, 0 count for it's a new record. 1 counts for it's a new list of level 1, and 2 means it's a new list of level 2. So actually, 0 means it's a new record, 1 means it's a new entry of in the list of level 1, and 2 means it's a new entry in the list of level 2. So here, 0 means new record for this one, and then we have 2, 2 to mean we're repeating in the second list, and then we have a new list at level 1, so we put 1, and then the next ones are repeated in level 2, so we keep this information, and so on. So here we have a new record, new list at level 1, because we have only 1 element in the first list, and then new element in the list of level 2. So that's how we capture repetition level. And the main thing is now we converted that to a list of integers that we know are small, and we can use bit packing on that because we can store it on 2 bits, and we can use run length encoding because there's going to be some repetition in there. Like if you have always list of 1 element, it's always going to be 0, so it's going to compress really well in run length encoding, and so on and so forth. And same thing for the definition level. If it's optional, but it's actually always defined, you're going to have only once in this column. So it's going to compress really well in run length encoding. Yeah.
How deep can this go? Like, and how does it work on more heterogeneous data? Let's say it has some tree, it has a lot of heterogeneous data.
So it needs to be strongly typed. So if you have heterogeneous data, you need to define separate fields. You know, if you have like, you're thinking like a union type, like, I don't know, if you have JSON and sometimes it's an int, sometimes it's a structure.
Like really deep nested type of thing, right?
So it can be really deeply nested, but it has to be formally defined, so that this field is this type, and then this field. So you can't have like recursive typing. You can't say this is a node. You can't define a type which is a node, and that refers to other nodes, because that's like the type is recursively defined, and that means there's no bound to the depths of the tree. This needs to have a fixed bound to the depths of the tree.
Like a clear grammar.
Sorry?
Like a clear grammar.
Exactly, exactly. So like the Swift is like that. Avro has the notion of recursive types, so that's not going to work, because now you can have, when you define the columns, every primitive type is a column, and the column is identified to the path to that primitive type. So if you have a recursive type, you have an infinite number of columns to that definition. But usually you can define your schema in a different way, right? If you have a recursive type, if you want to define a tree, instead of saying I have a node that contains some nodes, you say I have a list of nodes, and each node is followed by its children, and has a field that says how many children it has. So it's the same thing as doing like, you do a depth first traversal, you write all the nodes in that order, and by keeping track of how many children each node has, when you read back, you can get your tree back. And, so yeah, the constraint is you need like a fixed, you need to be, your schema has to be expressed as a fixed tree.
And how easy to modify? Let's say you knew some types, and later on you want to add some new types. Can you modify it?
Yeah. So it's all at the file level. So if you write a new file, the new file can have a different schema. And then when you read them all, what we do is we merge those schemas at read time to expose a tuple with a schema of what you're reading. So the constraint is those schemas have to be compatible, right? You can't, if you rename a field, it's going to be seen as two different fields in that case. If you change the type of a field, it's going to complain and refuse to load the data. Yeah, you can't change the type of a field. You can add, basically it's a typical thing. You can add fields to your schema and it's going to work.
I think this maps very nice to strong type languages like Haskell, for example. I think that will work really well.
Yeah, so it works well for Swift, for protocol buffers. Avro, you have to be careful with recursively defined types. And for Pig and Hive, that works too as well. Those types. Avro, I think, is the only one from one I looked at that has this recursive type definition. Also, so as you're probably aware, there's also arc5, which is included in Hive 11, which has similar features. And it just happened to be a concurrent work, right? We worked on those things at the same time, and then they were published later on, both of them. So arc5 is basically kind of having some features of supporting nested data structures, and it does it in a slightly different way. So the way we store the nested data structures is by having a repetition in definition level in one column per type. In Arc, it stores it differently. So you have one column per node in the tree, basically, because there's going to be a column per list, and it contains how many items in the list, and same thing for the map, and how many items in the map. So it's like different ways of storing the data. So it's just different approaches to storing this. So from the API standpoint, we have two APIs. One is to iterate on fully assembled record. So we implemented the algorithm in the Dremel paper when you build a feed state automaton to build a projection of the column. So you tell it which column you need to access. It's going to reconstruct the record accessing only this data. So it's going to recreate the same records, populating only the fields you need to access and reading only the columns for those. So you give it any, so from those examples above, right, you could build any of those subset of the columns. And that's what we integrate with Hive and Pig and Strift and Avro to reconstruct the records. So you can actually, if you wrote with Strift or Avro, you can also read back with Strift or Avro and have only a subset of the fields populated. And same thing for Pig and Hive. And the lower level abstraction, that is where the record assembly is built upon, is at the column level, and that's the one you would use if you wanted to implement vectorized execution engine. And the vectorized execution engine evaluate expressions on a column per column basis instead of row per row. So instead of evaluating, like if you have A plus B plus C, instead of doing it at the row level for each row, you do it at the column level, you do A plus B, and then once you've done that, you do A plus B plus C in a column fashion. And the advantage of doing that is it's much more efficient from a processor pipelining point of view, because now the processor, because you have a much simpler expression, is going to fit much better in the processor cache. And the pipelining, if you're reducing the number of if then else, let's say you're doing an or an and, it's much more predictable and to optimize execution. So the example A plus B plus C may not be very good because you probably want to evaluate all of them at once because they would fit in the processor cache anyway and they're very simple. But if you have more complex expression, then you express them, you evaluate them a column at a time and materialize the intermediary data, as opposed to evaluate each row completely. And so if you have already a columnar format, and the data is columnar, it becomes much easier. The data is already like that, and you evaluate your expression like that. And you can save, make the processing go faster thanks to that. And then you also have things like CMD operation if you're doing processor stuff for vector operation. So as I was explaining, it's already integrated with Strift, Hive, Pig, Avro. And this is done by having an event-based API. So the API is like start tuple, add field, add value, end field, start field, add value, end field, and struct. And so thanks to this event-based API, we can integrate with materializing different type of object depending on the framework that is being used without having to do double conversion, right? You want to avoid having a generic data model that you materialize the data to, and then you convert it to like pig tuples or Hive records or Avro records, right? So instead, we have this event-based API that is implemented for Hive, Strift, Avro, Pig, and Impala also has implementation, but it's using its own APIs.
Sorry, not clear. So you mean you don't need to predefine a structure in those environments? You just add them dynamically as happens, or what?
Yeah, so we have a bunch of submodules in the project. When there's a common implementation of the assembly algorithm, and that's implemented once, and then we decouple the actual materialization of objects. What's the type of your object? Like what you're doing a new tuple in Pig or a new Avro record in Avro, that's decoupled, right? So that when we do the integration with a different object model, we actually directly use that object model, right? It gets plugged into the assembly algorithm. So yeah, it's part of it's just a way of organizing the code so that we have a generic implementation of the assembly, but decoupled from the actual object model that is being materialized, so that it plays well with different environments. And so it's already integrated with all those things, and that's what makes it play well. One of the goals was to play well with, you have, you import your data in the system and you write it usually from a different thing that you use it to query, right? You use Hive to query, but usually import in your Hadoop cluster from different environments. You could have a MapReduce job, you're writing files from different environment, and you're using some abstraction. So at Twitter, we use Strift to encode the events that comes from the front end. At LinkedIn, they use Avro for that. So save the data as arrow, we save the data as strip. So when you're converting, usually don't do it from the system you use for query. So that makes it interact nicely with all those schema definition, and then it converts it to Hive and Pig, and that's easy to query and analyze. And so, quick pass on the encoding. So bit packing I talked about. You know, if you want to encode 132002220, knowing that the maximum value is 3, you know you can encode it on 2 bits. So now you encode it as 2 bytes with the value in binary. So that's bit packing. If there's a lot of repetition in the data, then if you have 8 ones in a row, you encode it on 8 bytes, on 2 bytes, one with 8, one with the value. Right? So that compresses very well, like things like the definition level, when it's actually, the data could be very sparse, so it's mostly undefined, so you have a lot of zeros, it's going to encode that way. Or it's always defined, so now you have a lot of ones, and it's going to encode very well. Like a million zeros, you know, just 1 million zeros. And we use a hybrid between bit packing and run-length encoding for that. Dictionary encoding I talked about, and that's the format is defined in a way that it's extensible, so that you can add encodings without breaking backward compatibility. Right? As opposed like RC5, for example, doesn't have really way of extending the format. So it's relatively new project, but we have already a bunch of contributors. People from various companies have contributed different parts of it. Obviously from Twitter and Cloudera, but also Criteo, which is a company that does ad targeting, and Stripe, and people from Parquet Amplified and LinkedIn have been contributing to the project. So, you know, we're trying to stimulate contribution by giving good reviews and actually merging the patches that people propose. And that's a lot of work, but that, you know, usually it's a good investment because, you know, if you let people know that their patches are actually committed and, you know, you're trying to give them good reviews so that it fits in the framework, then people contribute more and they feel better about using it in their stack. And so Parquet 2.0, so basically it's not a rewrite of Parquet, but as we're adding more encodings, you know, you won't be able to read Parquet 2.0 files with Parquet 1.0, but you'll be able to read the old file with a new library. So we will give it a major revision. So we're adding more encodings, and the goal is to take advantage of lightweight compression by good encoding. If we know more about the types, if we know that it's an int or it's a string, we can do better encodings and more efficiently because it's a columnar format. And it's going to be much faster than doing the heavyweight compression that is trying to find patterns in your data, like give them as a byte array. Like. So adding delta encoding, so that if you have time series or like, you know, integers when you're going to have like a lot of numbers that are close to each other, it's going to encode much better. And we're doing that for integers and strings. And also improve encoding for strings and Boolean. We're also adding statistics so that in the footer you have things like maximum value, minimum value, how many null values, these kind of things. And that enables predicate pushdown when you're doing a filtering of the data. Like I talked about it before. If you have a filter when you say I want everything with A, where A is smaller than 1, and it's for this for group, the maximum value, the minimum value of A is 2, then you know you can skip the entire row group. Right? So this kind of predicate pushdown that Pig and Hive have features to do predicate pushdown. Usually they're used for when you do time partitioning, right? You know you're reading only this partition for this hour because that's what the time feature says. But you can also use that for all the features. Like if you want everything where, I don't know, the status is 1, then you can skip a whole bunch of row groups. So now we have the advantage of reading only the columns that we want, but also only the row groups that actually contain data that will match the feature. And also we're working on the new page format. That's also the advantage of formally specifying the metadata is we can, and we use Swift for describing all the metadata. That way you can extend the format, add new page formats, and still be backward compatible. So yeah, we're paying a lot of attention as being able to be backward compatible, and evolve the thing, and all that. So next step is how do you use it and how do you contribute to the thing? So it's all on GitHub. We have a Parquet.io, but that will take you to the GitHub page. It's github.com/Parquet. We have entered a certain number of tickets with label pick me up. There are different difficulties. There are some things that are relatively simple, some things that are more advanced. But as we're defining those new encodings, we're also, we want to make sure people that want to contribute can find tickets that they're going to do, and it works. And it's like you put a wish list. It's like a letter to Santa. You list the things you want, and one morning you wake up, you look at your inbox, and oh, someone just implemented that. Thank you. Let me review it. Yeah, looks good. GitHub is magic. You like it? Just hit merge. It's in master, and next thing. And that actually works. People do stuff. People want to contribute, and they do some tickets that we label. And also sometimes people come up with things like, okay, I didn't think of that, and they have an idea, they want to do something, submit a pull request. Those usually take more time because, yeah, I didn't think of that. I just need to write my head around that thing and figure out, how we want this to work with the existing code. But that's awesome. You look at your repo and then pull request from it. Any more questions? Yeah.
I think you said something about your writing pattern. You're getting, like if you have log data for these accesses you talked about, is it coming directly from that system into the Parquet format? Is it coming through a kind of more transactional system?
No, yeah, so it's coming through Scribe. So Scribe is basically, you have services and you send event to them, and Scribe is going to write them into files.
Mm-hmm.
So basically the front end, you have like many machines that writes to a smaller set of Scribe machines that receive events from the instrumentation. It writes them to files, so it's like event-based at that point. And it's not writing directly to Parquet because the goal is to write to disk as soon as possible. And it's committed to disk, so the Scribe aggregators just like write to disk. And so there's a separate step that reads that and converts to Parquet. Consolidate all those files because that creates many small files. I mean, small from the Hadoop point of view. And you want to consolidate them and write. So the way we do it is we have a hourly partition every hour. So like every hour you have a new hour of data showing up in the cluster.
Do you keep the Parquet format? You no longer keep the sort of Scribe little files. You convert that to an hourly Parquet format, and that's what you run off.
Yes.
Okay.
You mentioned the org file. Any performance metric comparisons been done? Or?
A little bit. We are not. So org is part of Hive, so you can use it in Pig through Edge Catalog. The downside of doing that is you have extra conversions happening under the hood because it reads from the Hive serially, turning it into a big tuple, so you have extra conversions happening. We at Twitter haven't run a performance comparison because we're already using Parquet, and we would need to do all the plumbing to make it work with org. There has been some numbers, so in some case it's about the same. In some cases, one is better than the other. They're pretty much in the same ballpark. I think the Criteo is working on a benchmark to compare those. So Criteo has been doing the Hive serially. They're a Hive shop, and so they're doing the comparison with org, between org and Parquet. It's going to be similar, I think, in terms of performance. The big difference, I think, on on our point of view, we wanted to have something that is very agnostic to the platform, right? That's going to integrate well with many things. And I think the focus of work is to make Hive better. So it's going to integrate more tightly with a Hive type system, which is, depending what you're using, maybe it's better to be more tightly integrated with a Hive type system. But then now it's like you use it inside of Hive or outside of Hive through HCAP. Obviously, I like Parquet.
How easy is it to go from JSON to, if you had like a bunch of JSON documents, would you need a schema for them?
Yes, so Parquet is a schema first format, right? You can't write anything if you don't know what the schema is, because at the beginning it's going, it's going to create, you're going to have a string per column, right? And it's going to create, to encode based on those columns. So you need to provide a schema first. So if you have a bunch of JSON, you need to, we don't really have a generic, you could provide a schema and just like some kind of JSON abstraction, and we don't have yet like a generic way of writing JSON to Parquet. What we have right now, you could define either an arrow or a strip, or even I've seen people doing using the big tuple abstraction to write some MapReduce from some text format. So you could do that. You could also contribute some kind of JSON adapter, because it's not that hard, right? You just need to be able to provide a schema. So for all those integration, we have a converter that converts from, like say, pig schema or Hive schema or Swift or arrow to the Parquet schema, which looks like protocol buffers. You define the schema, and then you just need to be able to call those event-based methods corresponding to that schema, right? You
So
say start field, add value, and
would you also need to guarantee that like the arrays don't have like value types?
don't have, yes. It has to, the data has to match the schema you're providing. You can turn on, there's an optional schema validation. So if you know what that your data is according to schema, you can turn off schema validation is going to write. But it may generate broken data if you don't match the schema, because now you will have nulls where things you say it's required and is going to fail somewhere. Or you can turn on schema validation and it's going to actually verify validating the schema you've given. But you have the overhead of doing schema validation.
It's on a write, the schema validation occurs on the write.
Yes. But you need to turn it on because it's relatively expensive. I mean,
we could structure data. Let's say, to give example, we have some JSON or XML that has pretty well-defined areas, but areas you don't really know how they are defined. Can you define a schema which has some optional fields or some like type of any?
So you can't. So the way you do type of so in Avro you have the notion of union, right? So you say this field is type A or type B. And the way we do that is we actually define two fields. It's like name of the field underscore A or name of the field underscore B. And it's one of them, they're both optional, and only one of them is going to be populated. So that's how you could encode union. Because it needs to be well defined all the way. It needs to define all the types, but it's going to be good at compressing sparse columns. Right, so that's the idea, is when we're going to read, when you read those two columns, and they all have the data for the thing.
I can see the benefit of this from typing that as well, but sometimes at the beginning, at least when you start, maybe you don't really know well how your structure looks like, so over time you can iterate and structure your data, but when you start with it, you have some kind of weaker typing, maybe like a penny or whatever.
Yeah, but the whole encoding mechanism, right, it's all based on the fact that you know what the type is. So what you can do is, so there are two ways you can address that. One is you change the way the data is collected so that there's like type checking, right? You can like strong typing, you define the schema first, and then you know that everything is according to schema. Or you could also do two passes on your data, right? You could do a first pass. It's relatively easy to do a MapReduce job, and it's going to extract the schema from the data. If you can read the data, then you can do you can have a MapReduce job that is going to infer the schema from the data and then write from that.
So is Parquet providing that, or?
We have no. It's just we have like a big UDF that kind of generates JSON to that and gives you a summary of your data. We don't have something that extracts the schema from the data. It's kind of specific to the format itself. Right? You would have to make one. We could have something kind of generic. You can produce a schema for each object and merge it. Actually, yes, we have that. We have a method in the schema. We have a method to merge two schemas. So if you have a mapper that generates a schema for a given record, then you do a combiner that's going to merge all those schemas together. And the reducer merges these intermediary schemas. In the end, you have the schema for your data. So if you can produce a schema that each record matches to, you can generate the union of all of that. You will have to do some special case if the type changes and to deal with union. Yeah, something like that.
You have some branches missing and stuff like that. I suspect it may not be that easy.
So you can have optionals anywhere, right? You can define everything optional. That's fine. If you don't know if the field is always going to be there or not, you can define everything optional. And it will compress really well, right? If it ends up being defined all the time, then the runlines encoding will compress the nulls really well. Or like not any nulls really well. So in that you don't know the type of the thing, or you don't know if they're always defined.
You know, let's say you have a structure, right? And in that, you can have some subtypes which you know they are there, so you can define the type, etc. But you have some types which maybe or may not be there, so it's optional, or you may have even some things you haven't found, like the example you gave before, for example, when you merge and check what's happening, right? That would be a good way over a predefined set of data, right? But you may have some new data, which may have some new subtypes which have not been defined before. So how do you deal with that? If you don't have a way to have some optional field, then
Yeah, you can do optional. They can be optional, but you need to know beforehand what type it's going to be.
You said you could add fields and you can make them optional. It sounds like the difficulty is changing existing field types. That's kind of the problem.
Well, each file has its own schema, so you can, every file can be have a different schema altogether. When you read everything and you want to integrate with something that expects uniform schema, then you need to be able to merge those things together and expose it as a unified format. So what we're doing, we have some logic that merges the schema, so you can read the files independently of any metastore, and we're going to merge all those schemas together, assuming there's no conflict, right? You're not reusing the same name with a different type. So as long as you don't change the type of column, then you're fine. If you have things like a metastore, then you can provide a schema and say that's the schema that I want, and it's going to make sure that individual schemas fit into that schema you want. Meaning the types are the same, or
And talking about the merging and stuff, now let's go ahead. In RDF, for example, they use this unique, this way of identifying fields, right, by using the URIs, right?
Mhm.
So they have something equivalent in there, so when you merge things, like, it makes sense. When you merge these global entities,
so in
let's say you have data coming from multiple sources, right?
Mhm.
So they refer, some of them can be joint and common, so they have a way to, let's say, uniquely identify each element in there, so when you merge things, they merge meaningfully.
I don't know. I'm not sure I fully understand
RDF, for example, right?